Today we're talking about section 2.1, limits and continuity. And we're going to talk about how we calculate average and instantaneous speeds. We're going to talk about limits of different function values and then applying some properties of limits. It's going to take you back to some of the pre-calculus stuff we talked about at the end of last year. So when we talk about average and instantaneous speed, the first definition says if we have a function y equals f of t, and that represents the distance or the position function of a moving body at time t, then the average rate of change or the average speed is the ratio of some sort of a length with respect to some sort of unit of time. And so typically how we've seen this in the past is we've got some sort of change in y value with respect to some sort of change in time. So in this case, it would be this change in a y with respect to the change in t. So example 1 says that we've got a rock that breaks loose from the top of a tall cliff, and they want us to find the average speed. So I want you to emphasize this part. This word average is going to be really important to us. Average is going to remind us that this is just algebra 1 slope. And so my key here is always this A, and it's the same as A for algebra 1. We're going to be talking about average speed during the first 2 seconds of the fall using the formula 16t squared. So if we're going to find average rate of change or average speed from the first 2 seconds, that means I need 2 ordered pairs, one at time 0 and one at time 2. So at time 0, 16 times 0. And at time 2, 2 squared is 4. And 16 times 4, we get 64. So our average rate of change is 64 minus 0 over 2 minus 0. So 32, and then our units are important here. So they told us that, well, they didn't really give us a length unit, so we're just going to say feet per second. And so it says we can also talk about instantaneous speed or instantaneous rate of change. And to do this, we have to use the idea of a limit. So when we talk about this instantaneous speed of a rock at time 2. So now we don't have 2 ordered pairs to find the slope. So this is where I know last year you were introduced to derivatives, but for right now we can't use any of those derivative tricks. We have to really do the understanding and the limit definition that we need to talk about. So we need to find, starting at time 2, and we want to just move away from 2 just a little bit. So we're going to say the second time is 2 plus h, and h is going to be just a little bit further away. So again, we need our 2 ordered pairs. So 2 and 64 we already know from up here. But this other one is 2 plus h. And if I'm plugging in 2 plus h, my y value then, if I'm using the same formula, if I replace this t with 2 plus h, I get 16 2 plus h squared. And we're just going to leave it like that for right now. So now when I do y2 minus y1 over x2 minus x1, we get 16 2 plus h quantity squared minus 64 all over x2 minus x1, 2 plus h minus 2. So these 2's end up canceling out, and I'm left with just the h on the bottom. Now here I have to distribute this. I want you to take a second to distribute that. All right, so when I do 2 plus h squared, we have to be really careful to not just call it 4 plus h squared. We have to actually do some distributive property. It's 2 plus h times 2 plus h, so we get 4 plus 4h plus h squared. And then I use the distributive property. And so now at this point I can see these 64s cancel out. And then with the 64s canceling out, now I'm left with just this part, 64h plus 16h squared all over h. Everything's got an h in it, so I'm going to go ahead and take an h out of every term. And so now this idea of a limit, we're trying to figure out, we didn't really want this h in here in the first place. We wanted just at time 2. So I want to try to make that h go away. I want that h to approach 0. So we can say, all right, we want this limit as h approaches 0. And so notice my new equation now, limit as h goes to 0, all I have remaining is 64 plus 16h. When I had an h on the bottom, I wouldn't have been able to plug in because we can't have a 0 on the bottom. So now when I plug this 0 in, as h goes to 0, this term goes away, and we are left with 64 feet per second for our instantaneous rate of change at time 2. Now, this entire concept is completely done in chapter 3. So I just want you to have kind of a general understanding of it. Please don't panic about this definition yet. We're going to be doing a few more practices with this type of a problem, but this stuff shows up in chapter 3. So that definition of a limit, here's kind of your anatomy of a limit. This is red, the limit of f of x as x approaches c is equal to some sort of a limit. So in example 3, it says use your graphing calculator to graph the function sine of x over x and use the graph to estimate the limit of that function as we approach 0. So take a moment and graph it on your calculators. So here's what my picture looks like. And just to be clear, you need to make sure your mode says radian, not degree. Everything in this course is going to be in terms of radians. I apologize to those of you in AP Physics. Everything in there is in degrees. So you're going to have to be good about switching your calculator back and forth. So here's what my graph looks like. And right now it's kind of hard to determine, but I want to look at what is that limit as we are approaching 0. So right now it appears that that limit is about 1. So I want to kind of use the table to help me out. And right now my table is going up by 0.5s. And so you can notice that as we approach 0, it looks like it's getting closer and closer to 1. But something magical on your calculator, you can change how your table is set up. So we're going to hit second and then table set. And I'm going to have my table start at -1, but I want my table to go up by 0.1s so that I can get a little bit closer to 0. And then I'm going to go back to my table. And so now I can kind of creep up on 0 a little bit more. You can see it's getting closer and closer to 1. And then, of course, there's an error because we can't divide by a 0. And then let's see on the other side. Yeah, it's pretty symmetrical. And it looks like as we move closer and closer to 0, my limits are getting closer and closer to 1. So we would say the limit of sine of x over x as x goes to 0 is 1.